A building rises 12 stories. Inside, a metal car moves between floors. It does not move by itself. Someone stands at the controls, hand on the lever, watching the gate, the indicator, the opening ahead. The car stops where the operator places it. It moves at the speed the operator allows. Every trip upward depends on this presence. The building cannot function without it. The elevator car is a metal box suspended on cables. It has no mechanism to select its own destination. It has no sensor to align itself with the floor. The door does not open automatically. The car moves only when the operator closes the gate, engages the motor, and pulls the control lever. Early electric elevators use a simple circuit. Power flows to the motor when the lever is moved. The direction of travel depends on which way the lever is pulled. The speed depends on how far the lever is moved from center. There is no preset stop point. The operator must judge the distance, the momentum, the deceleration needed. The car will continue moving until the operator returns the lever to neutral. If the operator misjudges, the car will pass the floor or stop below it. Passengers will step into a gap or onto an uneven surface. The operator must correct this by reversing direction and making a second approach. The control is entirely manual. The building has no central dispatch system. Each elevator operates independently. The operator receives no signal from other floors. Passengers enter the lobby and wait. When the car arrives, they step inside. The operator asks for their destination. The operator closes the gate, moves the lever, watches the floor indicator. The car begins to rise. The operator feels the motion through the floor, through the lever, through the sound of the cables and the motor. There is no automatic brake. If the operator releases the lever too quickly, the car will jolt. If the operator does not stop the motor in time, the car will overshoot. The task is not dangerous if performed correctly. It is simply constant. Every floor requires the same sequence. Close the gate, engage the motor, pull the lever, watch the indicator, slow the car, align with the floor, open the gate. The operator repeats this sequence dozens of times each hour. The elevator does not rest. The operator does not rest. The building depends on this continuous presence. The control panel is mounted inside the car, within arm's reach of the operator. The primary control is a brass lever, approximately 12 inches long, hinged at the base. The lever can be moved forward or backward from a central neutral position. Forward engages the upward motor. Backward engages the downward motor. The degree of displacement controls the voltage supplied to the motor, which controls the speed of the car. A gentle pull moves the car slowly. A full pull moves it at maximum speed. The operator must learn the resistance of the lever, the response time of the motor, the weight of a full car versus an empty one. A loaded car accelerates more slowly. It requires more distance to stop. The operator adjusts by pulling the lever earlier, holding it longer, returning it to neutral sooner. Next to the lever is a floor indicator. It is a vertical column with numbered markers. A pointer moves along the column as the car moves. The pointer is connected to the cable system by a mechanical linkage. It shows the approximate position of the car between floors. The operator watches this indicator constantly. It is the only reference for vertical position. The car has no windows. The operator cannot see the floors passing. The operator must trust the indicator and must learn to interpret its motion. The pointer does not stop precisely at the floor marker. It drifts slightly as the car settles. The operator must anticipate this drift and stop the car just before the marker, allowing momentum to carry it into alignment. This requires practice timing. To the left of the lever is a brake handle. The brake is a mechanical clamp that grips the guide rails when engaged. It is used to hold the car stationary while passengers enter and exit. The operator pulls the brake after stopping. The operator releases the brake before moving. If the brake is not fully released, the motor will strain and the car will jerk. If the brake is engaged while the car is moving, the car will stop abruptly and passengers will lose their balance. The operator must coordinate the brake and the lever smoothly. There is also a gate control. The gate is a folding metal barrier that closes the entrance to the car. It must be fully closed before the motor can be engaged. Some systems have an electrical interlock. If the gate is open, the motor will not start. Other systems rely on the operator to check the gate manually. The operator pulls the gate closed, latches it, then moves the lever. The sequence must be followed exactly. The operator stands in the same position for the entire shift. The shift lasts 8 to 10 hours. The operator's hand remains on the lever or near it. The operator's eyes remain on the indicator. The work is not physically strenuous. It is mentally continuous. There is no moment when attention is not required. A distraction of 2 seconds can result in a misaligned stop. A hesitation can delay a floor full of passengers. The operator must maintain the same level of precision at the beginning of the shift and at the end. The controls do not change. The task does not change. Only the operator's fatigue changes. The elevator operator is employed by the building. In office buildings, the operator wears a uniform. In hotels, the uniform is more formal. In department stores, the uniform matches the store's style. The operator is visible to passengers but is not expected to speak beyond necessary instructions. Passengers enter the car and state their floor. The operator acknowledges with a nod or a brief word. The operator closes the gate and begins the ascent. During the trip, the operator stands facing the controls. Passengers stand behind or to the side. The space is small. In a typical car, 6 to 8 passengers stand comfortably. More than that and the car is crowded. The operator is aware of the weight. A heavier load requires more careful control. The operator does not socialize with passengers. The operator does not make conversation. The role is functional. Passengers expect smooth travel and accurate stops. They expect the car to arrive quickly when called. They expect the operator to know the building, to anticipate traffic, to move efficiently. If the operator misaligns the car, passengers must step over a gap or onto a raised floor. This is noticed. If it happens repeatedly, complaints are made to the building manager. The operator is expected to perform without error. In some buildings, the operator is expected to announce the floors. As the car approaches each stop, the operator calls out the floor number and the departments or offices located there. This is common in department stores. The operator says, "Third floor, men's furnishings, shoes, sporting goods." Passengers who are unfamiliar with the building rely on this information. The operator must memorize the layout. In a large department store, this can mean dozens of departments across 8 or 10 floors. The operator must remember which departments are on which floors and must update this knowledge when the store rearranges. The operator must also manage the flow of passengers. When the car is full, the operator does not stop for additional passengers. When the car is ascending and a passenger requests a lower floor, the operator may ask them to wait until the car descends. This is not a rule. It is a judgment. The operator decides based on the number of passengers, the urgency of their destinations, the time of day. During peak hours, the operator may make express trips to the upper floors, skipping intermediate stops. This reduces wait times for passengers on higher floors. It also reduces the number of stops per trip, which reduces wear on the motor and the brake. The operator makes these decisions without instruction. There is no dispatcher. There is no schedule. The operator simply responds to the demand trip after trip, hour after hour. Passengers do not thank the operator. They exit the car and continue to their destination. The operator closes the gate and waits for the next call. The work is isolating. The operator spends the entire day in a small metal box, moving between the same floors, seeing the same walls, hearing the same sounds. The only variation is the passengers. They change. The task does not. Buildings grow taller in the early 20th century. Steel frame construction allows structures to rise beyond 10 stories. Office buildings reach 15, 20, 25 floors. Hotels and apartment buildings follow. The higher the building, the greater the demand for vertical transport. A 10-story building can function with 2 elevators. A 20-story building requires 4 or more. Each elevator requires an operator. Each operator works a full shift. Buildings must employ multiple operators to cover all hours of operation. In a busy office building, Elevators run from early morning until evening. In a hotel, they run continuously. The number of operators increases with the height and occupancy of the building. A single large building may employ a dozen operators across multiple shifts. The work becomes more complex as buildings grow. In a 20-story building, a trip from the lobby to the top floor takes longer. The operator must make more intermediate stops. Passengers on upper floors wait longer for the car to arrive. Buildings attempt to manage this by assigning elevators to specific zones. One elevator serves floors 1 through 10. Another serves floors 11 through 20. This reduces travel time but requires coordination. Passengers must know which elevator to use. The operator must enforce the zone. If a passenger requests a floor outside the zone, the operator must direct them to another car. This adds confusion and delay. Manual operation also limits speed. An experienced operator can move a car smoothly and quickly, but there is a ceiling to how fast a human can react. The operator must watch the indicator, judge the distance, begin deceleration, and stop the car within a margin of inches. At higher speeds, this margin shrinks. The operator cannot react quickly enough. Buildings address this by limiting elevator speed. Cars move at a safe, controlled pace. This means longer trip times. It also means more elevators are needed to serve the same number of passengers. The cost of employing operators becomes significant. Each operator is paid a wage. Each operator requires benefits, breaks, and coverage. The building must maintain a staff large enough to operate all elevators during peak hours. If one operator is absent, the building must find a replacement or take an elevator out of service. Passengers complain, traffic slows, the building's function is reduced. Buildings also face the problem of consistency. Operators vary in skill. Some are smooth and precise. Others are abrupt or slow. Passengers notice the difference. They avoid certain elevators. They wait for the operator they trust. This creates uneven demand. One elevator may be crowded while another sits empty. The building cannot control this. The only solution is training, but training does not eliminate variation. Human operation will always vary. Manual elevators also require more maintenance. The constant starting, stopping, and braking wears the motor and the cables. The operator's technique affects this wear. An operator who accelerates too quickly or brakes too hard increases strain on the system. Over time, this leads to more frequent repairs. The building must balance the cost of operators with the cost of maintenance. Both are high. Both increase as buildings grow taller. Automatic elevator systems begin appearing in the 1920s. The first systems are simple. Passengers press a button inside the car to select their floor. The car moves to that floor automatically. It stops without operator input. It aligns itself with the floor. The door opens. The system uses electrical relays and mechanical switches to control the motor and brake. The technology is not complex, but it is unfamiliar. Buildings are cautious. Early automatic elevators are installed alongside manual ones. Passengers can choose. Many passengers prefer the manual elevator. They trust the operator. They do not trust the machine. Automatic elevators stop roughly at first. They overshoot or undershoot the floor. Passengers must step over gaps. They complain. Buildings adjust the systems, refining the timing and the sensor alignment. Gradually, the automatic elevators improve. They stop more reliably. They stop more smoothly than some operators. Passengers begin to accept them. Buildings begin to see the advantage. An automatic elevator does not require a wage. It does not require brakes. It does not call in sick. It operates consistently. One automatic elevator can replace one operator. A building with 6 elevators can reduce its staff by 6. The savings are immediate. More buildings install automatic systems. Operators begin to disappear. Some are reassigned to other roles within the building. Others are let go. The union resists. Operators argue that automatic systems are unsafe, that passengers need human judgment, that machines cannot respond to emergencies. Buildings respond by demonstrating reliability. Automatic elevators run for months without incident. Passengers stop noticing the absence of an operator. the resistance fades. By the 1930s, most new buildings are designed for automatic elevators. Older buildings begin retrofitting. The process is gradual but steady. Operators continue working in buildings that have not yet converted, but the number of those buildings shrinks each year. Some operators remain employed in high-end hotels and luxury apartment buildings, where personal service is valued. In these buildings, the operator is not just controlling the elevator. The operator is greeting residents, carrying packages, answering questions. The role becomes less about operation and more about service. But even in these buildings, automation eventually arrives. The cost is too great to ignore. By the 1950s, manual operation is rare. A few operators remain in older buildings that have not been updated, but they are exceptions. The profession is ending. The elevators themselves continue moving. The cables still pull the cars upward. The motors still turn. The floors still pass. The only change is the absence of the person standing at the controls. When an operator is removed, the elevator does not stop. The car is fitted with an automatic control panel. Buttons are installed for each floor. Passengers press the button. The car moves. The door closes by itself. The car stops at the correct floor. The door opens by itself. The passengers exit. The system works without intervention. Buildings that once employed a dozen operators now employ none. The elevator shafts remain the same. The cars remain the same. The cables, the motors, the guide rails remain the same. Only the control system has changed. Passengers adjust quickly. Within a few months, they forget that an operator was ever present. They forget that someone once stood in the corner, hand on the lever, watching the indicator, aligning the car with each floor. The task is invisible now. It was invisible then. The operator's work was not dramatic. It was simply continuous. When the operator is gone, the continuity remains. The building continues to function. Offices open, workers arrive, they press the button. The car arrives, they step inside, the door closes, the car rises, they exit on their floor. The elevator returns to the lobby. Another passenger enters. The cycle repeats. There is no ceremony when the last operator finishes the last shift. There is no recognition of the years spent moving between the same floors, standing in the same small space, performing the same task thousands of times. The operator leaves. The elevator continues. The building continues. Some operators find other work. Some retire. A few may have remained in the building in different roles, though there is no record of this. The profession simply ends. The elevators do not notice. Years later, a passenger might stand in an old elevator car and see the marks where the control lever was once mounted. A brass plate with holes, a faint outline on the wall, nothing more. The car still moves. The floors still pass. The building still rises above the street. People still move upward, floor after floor, without thinking about how they get there. The elevator arrives when the button is pressed. It stops where it is told to stop. No one stands at the controls. No one needs to.